All right, so how you guys doing today?
All right.
About, yeah,
Halfway.
halfway
Yeah.
up. So today we're going to talk about diffusion. So nominally we're talking about turbulence right now, but I need to derail and talk about diffusion by itself because I need it. I need just plain diffusion. Because for several reasons. One, because there is a diffusion-like operator in the Navier-Stokes equation, and that is important. And the fact that we understand the diffusion operator says that we really understand the right-hand side of Navier-Stokes equation. Also, turbulent diffusion behaves differently from regular diffusion and lets you mix things much more effectively. So I'm going to show you that too. Probably not get to that today. So what am I doing today? Where'd my chalk go? So the first thing, that's not the sheet I need. So I'm unhappy with my level of preparation for the day, so I apologize about that if this isn't my smoothest of lectures. I got really stuck on this one dumb math thing this morning when I was going through the derivation. I was like, wait, why does that work? And it took me like 20 minutes to sort that out, which ate up 20 whole minutes of other prep time that I had. So I'll show you where I got stuck, but the problem is it's like a dumb step in internal derivation that I believe that it's true because I know I've done it already. I didn't need to get stuck on it today, but I needed to get stuck on it because I'm going to show you guys. So anyway, okay, so the first thing I'm going to do is, let's start over here. We're going to talk about random walks. And I'm going to show you that that for a random walk, the expectation of the square of the number of steps of the distance that you have gone goes like the number of steps. So we're going to talk about this, and then we're going to take the continuous limit, and we're going to get Gaussians, e to the minus x squared over 2 sigma squared t. So we'll start with discrete random walks, then we'll take the continuous limit, and then I'll connect it to diffusion. I'm going to connect it to the del squared operator. Because this del squared operator does a whole lot of things. So this is how heat moves around. This is how viscosity mixes things. So del squared is a very important operator. And then, if I have time, I want to talk about the Green's function for del squared. And the reason that I want to talk about that is because having the Green's function means that we understand the solution space. So having the Green's function means that we can undo that operator. That means that if you give me a system and told me it got there by diffusion, I can undo that and tell you where it started. So the Green's functions are very powerful. And the fact that we have it for this means that we've completely characterized what kinds of things del squared can do, which makes it all the more puzzling why we don't have a good solution space for the Navier-Stokes equation. Okay, so also welcome to halfway through the semester. We got 15 weeks. And this is the 15th lecture. This has to be halfway mark. Hopefully there's not another hurricane. 3 in a year would be pretty rough. 2 in a year is pretty rough. Okay, so I am going to start off with, let's say I can take a random walk. Oh, hey, what's up, guys?
There they are.
I was late too, and you guys were even later.
We had an exam.
It's all good. Yeah, they mentioned that everybody was depressing a little bit.
Yeah.
How'd it go?
Coming from the VA.
That exam was extremely rough.
We just don't want to talk about it.
That's all right. That's okay.
It's
Well,
just-
let's do super bizarre math stuff today. Let me vamp for like 30 seconds while you guys get set down and find your objects. So today, just to recap, let me zip back a step because I haven't actually said anything. Today we're going to go through diffusion because diffusion is a process that we have really well characterized. Also, diffusion kind of feeds into Navier-Stokes equation. So we're going to talk about random walks. Have you guys haven't, I know I asked this already, none of you guys have taken StatMech, right? So have you guys seen Stirling? You have? Okay. Have you guys seen Stirling's approximation anywhere? No? That's okay. I hate Stirling's approximation, but we'll do it. It's just so long and horrible. But it's actually very, very useful because factorials are very, very, very large. So you need to deal with those. So we'll talk about that. We'll talk about all of these things. So we're going to talk about random walk. We'll talk about the continuous extension of that, which is where Stirling's approximation comes in. Then we'll connect it to Gaussian, and then maybe we'll talk about Green's functions. Okay, so the basic idea is M is my location that I can walk. So I only take steps of fixed size. This is like the Ministry of Silly Walks. My location is M, and I can move to the left with a probability P and to the right with a probability Q, which is equal to 1 minus P. Why is it equal to 1 minus P? Because probability has to add up to 1. And the only options I have are going left or right. In here, staying still is not an option, I guess. Wonder what that would look like. It's really kind of physically impractical, though, because nothing ever stays still. Okay, so I'm going to take n steps. N1 will be to the right. N2 will be to the left. So my position M is going to be N1 minus N2. That's how much left I go, time minus how much right I go, right? So if I assume I start off at 0, I move to the left, move to the right, I'm at some place. So N also equals N1 plus N2. So we also have, I'm going to write this over here. N1 equals 1/2 big N plus M. N2 equals 1/2 big N minus M. This is just a little bit of algebra to set things up. So if you just solve these two, you get these two equations. So that's just relating the two things. So the probability that I have gone N1 steps to the right and N2 steps to the left is going to equal something that I'm going to talk about in a second. Well, the count. We're going to count how many ways we can do various things, times P to the N1, Q to the N2. So the probability of having gone N1 steps to the left and N2 steps to the right, because N1 and N2 are a random variable. Really, there's only one random variable, so we'll simplify this. This doesn't have to be a two random variable thing. Is going to be P1 to the N1 times Q1 times Q to the N2 times the number of ways to do N1 and N2. Does that make sense? So if there's two ways for me to go to the right, but only one way for me to go to the left, then I got to wait to going to the right. So let's count the ways. So if I have, let's do this on this other board, and let's do it in chalk, in color chalk. So I have n objects, 1, 2, 3, 4, 5. How many ways can I arrange those n objects? I'm going to make a line. Oh, that didn't come out right away. I was expecting somebody to yell out.
And permutation.
The simplest thing. So let's think about, I'm just going to line these guys up in bins. How many choices? So I've got a bag with n things in it. How many choices do I have for the first one?
5.
What's that?
5.
5? Oh, let's just keep going.
Oh, and.
N? And then how many choices do I have? Now there are n minus 1 beads in the bag. How many?
N minus 1.
Then n minus 1, n minus 2, n minus 3. What do we call this? So we have n factorial ways to arrange n objects. Does that make sense? So this is the beginning of StatMech, right? Is this n factorial here? Now, some of these, now instead of doing what I just said, now I'm saying that I've got some of them are square and some of them are triangle. Right? I have n1 squares and n2 triangles. The squares are all identical and the triangles are all identical. So once I have picked up taken all my stuff out of my bag and lined them up, then I can switch all the squares, I can switch all the triangles. So the actual total number of ways that I have to arrange n things that are taken from 2 different populations is n factorial over the number of triangles factorial, because I can switch up the order of the number of triangles, times the number of squares factorial. So the actual number of ways to pick out 2 different sets of beads is n factorial over n1 factorial, n2 factorial. That make sense? Now, since I know, okay, now jumping back to here, I know that n2 is n1. I know that n1 plus n2 is big N. I can just rewrite this as n factorial over n1 factorial n minus n1 factorial. Does this make sense? How I got here? Have you seen this somewhere else before? No? This is the coefficient to a binomial expansion. So when I have x plus y to the n, expand this out with me. This might take a minute, but we can do it. So it's x to the n plus x to the n minus 1 y to the 1 plus 2 x to the n minus 2 y. Oh, actually, there's a 2 here. Let's do it specifically. Let's do x plus y squared. This is going to be x squared plus 2xy plus y squared. Right? I do it again. If I have x plus y cubed, this is x squared plus 2xy plus x squared y x cubed plus 2x squared y plus 2xy squared plus y cubed.
I think it's 3x squared y.
3x squared y? Okay, so anyway, you go through this process and you realize that the coefficients in front of these, the coefficients in front of your binomial expansion is this. It winds up being these. And there's a way to derive that. You can just trust me for now. But we're going to need the fact that if I have a polynomial, let's write this over here, x plus y to the n, this is the sum on little n equals 0 to big N of this formula, which we call n choose little n, times x to the big little n y to the big N minus little n. So a general binomial expansion has, so this we call n choose n, big N choose little n. So this notation goes along with this n factorial over n factorial times n minus 1 factorial. Let me keep my 1's consistent. Is everybody good with that so far? And everybody good with the fact that these things are in fact the coefficients of some binomial expansion. So this will become useful in a second. So, okay, so let's back up for a second. So now, the probability of going n1 steps to the right, given that I've taken n total steps, is equal to the probability that I'm at a location m, given n steps. So, because I can rewrite it as function of n1 or m, because I have these functions here, okay. So this is equal to n factorial over n1 factorial n minus n1 factorial, p to the n1, q to the n minus n1. So this is the probability, given this random walk, that you've gone to the right by n1 steps. Is the total number, choose the number you've gone to the right, times these two probabilities. Does that make sense, everybody? So now, what we want to do, we want to find the expectation value of n1. So the expectation value of n1. How do I find the expectation value given a probability distribution? Have you guys taken how many of you have taken a stats class? Only a couple. How many of you have never taken stats or anything like that? All right. So when I have a problem, let's talk about probability for a second. My very favorite classroom is the one in the basement of Keene. Some of you guys took some of you guys took Xscale with me. So I love these boards because they slide around and you can have some ideas and put them to the side, because I might need to come back to all of these ideas. But I got to talk about probability for a second. So given a probability p of x, this is a probability distribution, so this is a continuous function. If I want to know things about this, so I know that the integral of the probability has got to equal what? It has to equal 1. So this is just like a wave function. So this is just like wave functions in quantum mechanics. So the sum of the probability has to equal 1. And if I want to know something about this, if I want to know something about some quantity, then I have some f of x times p of x dx, and it'll tell me how often I actually do f of x. Because you take your f of x and you multiply it by the probability of that particular x, and then you add it all up, and you get the expectation value for this function. So if I want to know where I probably am, I need to do the integral of x, p of x, dx. Just like in quantum mechanics, when you want to make a measurement of something, you have psi, the operator you want, and then psi dx. So this is the same thing where, but because of the vector spaceness of quantum mechanics, you have to do the probability this way. But this is the same thing as saying this. Does that make sense? It just happens to be you get it out of the wave function this way, but that's the same thing that you're doing. So then the probability of, so this is the probability that you've gone to a particular point, but if I'm just drunk walking around the origin, what is the probability, what is my most likely place that I'm going to be? At the origin. I'm going to be likely at the origin. So I know that the average of x is 0, but the average of x squared, p of x, is not 0. That's about how far you've gone in total. So we're going to talk about these two things. So, okay. So let's sort out what the expectation value of my position n1 is. So we're going to look for the expectation value of n1 which is going to be the sum of n1 times n choose n1 p to the n1 q to the n minus n1. Oh, I'm sorry, I skipped a bit. I'm going to put it over here. I don't need these things anymore. So because of this, I know that p plus q to the n equals the sum on n choose little n times p to the n q to the big N minus little n. And I know that this equals 1. That makes sense? So why do I know that this equals 1? Because p plus q equals 1. So p plus q to the n is still 1. But I also know that p plus q equals the sum of all of my probabilities, which I know also has to equal 1, because that's how probability works. So what I'm going to do is now we're taking this sum, which I know goes to 1, and we're going to add it, we're going to stick an n in it. So here's this weird math stunt that works sometimes. And you'll see it in math physics. This is how you get, like, you can generate a lot of analytic integrals this way. So you've probably seen this stunt before. But what we're going to do is we're going to take p plus q to the n, and we're going to stick a u in here. And then we're just going to pretend that u equals 1. But we're going to pretend that u is something that I can do stuff with as well. So this equals the sum on n choose big N choose little n times u to the n, p to the n, q to the n minus n. But what I'm looking for is n. So what I want to find is this n here. So if I take a derivative of this thing with respect to u, which is 1, so I can do that because it's a stupid thing to be doing, it pulls down an n though. So if I say that, so I can say that this is equal to the sum on little n of d of u times d by du of n choose n, u to the n, p to the n, q to the n minus n. So I'm inserting a 1 and then taking derivative of a thing that I know is constant, so I'm not actually doing anything.
There's thunder over there.
So we can take this expression and realize that it's equal to this expression. So I just need to take, so to get the expectation value of n1, I just need to take u times d by du of p u plus q to the n, and then we'll evaluate u equals 1. Does that make sense? It's kind of a weird thing to do, but it works out and I can do it. So this gives me, when I do this, so I take d by du of this thing, it just brings down an n, and you get a p. So this is just equal to n times p times pu plus q to the n minus 1, but I know that that's 1 because u is 1 and p plus q is also 1. So the expectation value of n is equal to n times p. So that's the probability that you've taken n steps to the right. Is just how many steps you've total taken plus how many plus the probability of taking a step to the right. Times. So if I've taken n steps and the probability of going to the right is, if I take 100 steps, the probability of going to the right is 3/4. I've taken probably 75 steps to the right. Does that make sense? So through this weird math stunt, we get that the expectation value of going to the right is just the number of steps times the probability of going to the right. So now, this doesn't actually do us any good, because we know that the probability, that, like, you know, the probability of your position is ultimately going to be 0 in the end. This is just the probability of steps to the right. So if the probability is a half, then the number of steps to the right is a half of the steps that I've taken, and then clearly the number of steps to the left is also going to be half of the steps, and I have taken no net steps. So let's work out what the expectation value of n squared is. So we're going to pull a very similar stunt to this, but we're going to say u times d by dx, u times d by du of u times d by du of p u plus q to the n. So all I'm doing, so why does this work? This works because if I have u to the n, and I take d by du of that, and I multiply by u, I'm just left with n times u to the n. Right? You get a -1 from the derivative, and then this u brings it back. So I'm just left with n, and I haven't changed the function at all. If I want to bring down an n minus 1, then I just do that again, u d by du of that, and I get n squared u to the n. So this generator function kind of just spits out n's from this relatively arbitrary function that we've stuck in here. So we work out what this is, and you do a little calculus, and you find that the expectation value of moving to the right is equal to n times p plus n times n minus 1 p squared. So you can see that if you just do this derivative in your head. The first one brings down an n, and then the second one down brings down an n minus 1. So this is just a little bit of calculus. It's a little bit of calculus that I got stuck on for like 20 minutes this morning. So don't be stupid when you're doing this derivation like me. So the expectation value of moving n to the right is this slightly more complicated value. So the variance, sigma squared, which is the average of n squared minus the average of n squared. So this is the variance, this is the mean of n squared, and this is the square of the mean. So this is just the standard deviation like you're used to taking. Is equal to just n times p times q. So now we need to relate so this is the sigma squared on n, on the number of steps to the right that I've taken. So I can get the variance in the number of total steps that I've taken by just plugging in these formulas. And you're left with the basic result that the average number of steps that you've taken is proportional to n. Specifically, it's you pick up a 4 from the algebra and you get a p and a q. So the variance on the number of steps you've taken is 4 times n times p times q. So it just goes like the number of steps that you've taken. So your RMS distance away from the origin is going to go like the square root of the number of steps that you've taken. Does that make sense? So this square root process really comes in kind of all over the place. But isn't very useful because this is talking about taking discrete steps. And I don't have discrete processes, I have continuous processes. That's the whole point of the class. The whole point of the class is making continuous things out of discrete things. And I'm getting, these notes I'm getting from a thing I found online that actually describes these things, describes the things that I want to talk about in the order that I want to talk about them in. So I will put this up online these notes. So if I want to change this so that now I'm talking about position, I can say that x equals m delta x, where delta x is my step size, and t equals big N delta t, where delta t is my time quantum. Let's see, and if you do that, you do a little bit of algebra, and you get that x minus x bar squared, average of all that, is equal to 4 times p times q times n times delta x squared. That's it. Which we're going to call this 2dt, where we're defining d as 2pq delta x squared over delta t, linear and delta t. So my diffusion coefficient always goes like space squared divided by 1 time. Okay, so this gets us a space, but now let's get us an actual continuous process, because this is a quantized process. We want to get rid of the quanta. So we're going to write down Stirling's approximation. I'm going to write it down over here. So n factorial is much larger than e to the n. N factorial goes up very, very fast. So when I have an n factorial term, there's a lot of terms that you could throw out because they're way smaller. So Stirling's approximation says that the log of n factorial is equal to n plus 1/2 times the log of n minus n plus 1/2 the log of 2 pi plus stuff that goes like 1 over n. Here, let me point the camera at that real quick. You can't really read that on the screen. So, have you guys seen this big O before?
Order?
Yeah. Did anybody tell you what it means?
Order, like the order of terms?
Yeah.
Okay.
No, so that's, okay, so I'm not trying to be snarky, but that's really, so this big O notation has very specific math definition, where you make a series and your quantity stays below this. So there's a very rigorous math that goes along with this, but the way that physicists use it is like, oh, that's small stuff, we can throw it out. So it's of the order. So we physicists wave hands with it like it's our job. But there's a lot of math behind it, but we're physicists, we're squishy with the math. So this means order things that go like 1 over x, which means they're a lot smaller than things that go like n or whatever. So anyway, so if you take an advanced calculus or a higher order number theory or real analysis class, then you'll run into the actual definitions of big O notation. But for physicists, it's just, here's where we wave our hands. So Stirling's equation approximation says that. So what we have is, I want to write this up here again. P of m and n, let's write it this way. is equal to n factorial over n minus m over 2 factorial n plus m over 2 factorial p to the 1/2 n plus m q to the 1/2 n minus m. So this is, again, the probability of moving to the left, the probability of moving to the right, counting all the ways that you can do those steps in whichever order. Yeah.
So are those two over that?
What?
Are they like multiplied? Or is it added?
Oh, it's all multiply.
Oh.
Yeah.
That's n plus n on the p.
Yeah, p is n plus m, and this is n minus m. And there's a 1/2 for both of those. So I take the log of p of m and n, and I get the log of n factorial minus the log of n minus m over 2 factorial minus the log of n plus m over 2 factorial plus 1/2 n plus m times the log of p plus 1/2 n minus m times the log of q. Because logs break, multiplies, and divides into adds and subtracts. So then we take this gnarly thing and we plug it in for each of our log factorials, and we skip some algebra because we're going to mess it up. Yeah. Okay, and then we rewrite things. M we're going to say is the average of m plus the deviation of m. This isn't small. This is the thing that I'm looking for. So this isn't a delta that I get to throw out. Yeah, so I do this, and then I do a little bit of algebra, and I'm left with the log of p is equal to minus 1/2 log of 2 pi npq minus 1 over 2 sigma m squared delta m squared. Where I've skipped some steps to get to this much more simple derivation, but it's really just some algebra. So you plug in this assumption, and then you use the log expansion. Log of 1 plus x equals x minus 1/2 x squared. So this is just the Taylor series for log. So this plus some algebra gets you this formula here. So now when I exponentiate this, p of m and n now is equal to, all this turns into 2 over 2 pi sigma m squared, square root of that business, e to the minus 1/2 delta m squared over sigma m squared. So you get a Gaussian. So nature loves this form. Mathematicians love this form. Everybody loves a Gaussian. Because Gaussian is a thing you can do a lot of math with. It's a distribution that we understand all the moments for. It's and it naturally occurs through random mass processes. So there's a theorem Have you guys heard of the central limit theorem? Yeah? somewhat. So the central limit theorem says that everything goes to a Gaussian. Okay, it's a little more specific than that. But that's the upshot. If you have a random additive process and your process is independent and identical, then that process in the limit of large n gives you a Gaussian. So it has to be an additive process. You have to have a large number of n, and then you get a Gaussian. It's actually, n isn't that large, it's only a couple thousand. So math tells you that you're going to get a Gaussian, kind of regardless, because I know that I have set this up as a random additive process, so I know I have to have a Gaussian at the end. So that's part of why Gaussians show up all the time, is because nature likes to make them. It's easy for nature to make something look like a Gaussian. Okay, so that's the continuous limit. It's really just an application of Stirling's formula to the log of the n factorial. So this is a way that we can take this n factorial. There's really not a lot of analytic things you can do with the factorial. They're really kind of a hassle. But this way it takes the factorial and turns it into other analytic functions that you can deal with. So you'll see Stirling's approximation when you get to StatMag. You'll see probably this entire lecture again when you get to StatMag. I feel like it's worth going over again because so many processes have so many things have random processes like this underneath them, that I did this for walking in space between points on a lattice, but you could do this in any other kind of space where you're jumping between points. The same kind of thing works. These could be energy levels, these could be all kinds of things. Okay, so now we've seen that our continuous limit goes to e to the minus delta x squared over 2 sigma squared t. The t is baked into this sigma m. Yeah. So then the last thing we want to do is show this is the reason that I wanted to talk about this in the first place. Is because all of this is connected to the diffusion operator. Why? Let me show you something else. So I'm going to show you something that's called the master equation. And the master equation feels really dumb, but is incredibly powerful. There's a lot of things in physics that feel kind of dumb, like method of characteristics, that feels like, well, that's kind of dumb, but unpacks to this enormously powerful machine. So we're going to write down a master equation as well. So we want to find out I want to know how P of n, m, and n evolves with time. So given that I have this, what is P of m, n plus 1? So what I can say, this is what I want. So what I can say is that the probability of m, n plus 1 is equal to the probability, is equal to P times the probability of m minus 1 n plus Q times the probability of m plus 1 n. So I have my lattice. Here's m. The probability that I'm going to land in this spot is just equal to the probability that I start here and move that way, which is this. It's the probability of being in m minus 1 times the probability of moving to the right, plus the probability that I'm over here and moving that way. So that's Q, the probability of moving to the left, times however much stuff I have in Q, or however much stuff I have to the right. So the stuff that will move from the right to the left. And that's it. So state equals, yeah, so sorry, my squirrel brain has to work a thing out. Anyway, sorry. So let's do a little bit of algebra. So we're going to subtract p of m and n from both sides, and we're left with, and then we're going to multiply, and we're going to divide by delta t. So this is going to turn into p of m n plus 1 minus p of m and n divided by delta t, and that equals sorry, we also are going to do some stunts with some delta x's. So this turns into minus p times delta x over delta t times p of m and n minus p of m minus 1 n over delta x plus q of delta x over delta t times p of m plus 1 minus p of m n over delta x. So what we've done is we've subtracted my original state from both sides and rearranged the right-hand side by sticking in a p of m and n. So then, oh, I skipped a bit. So over here, let's talk over here for a second. Going back up real quick. So the average position, where am I? Is equal to the average of m times delta x, which is equal to n times p minus q times delta x. And so we're going to define a quantity v, which is the velocity, and this is p minus q times delta x over delta t. So it's just the difference in the probabilities times your units. So this is the drift velocity. So if I have this random process, I'm more likely to go one way than the other. There's going to be a net drift in the way that's more probable. So I can come over here. So what did I do? I started with just writing down what I want, p of m plus 1. And this has to be p of this times this. And then we insert p of m and n, which is the original step, and then we subtract from both sides. And we do a little bit of algebra on this right-hand side.
So on the right-hand side, basically you took the p of m n, and because it's multiplied with 1, which we can write as p plus q, we can put it in each of them separately, right?
Yes, you follow that? So let me do what he said. So I'm subtracting p of m and n from both sides. And I can rewrite this as p plus q times p of m and n. So I have a p of m and n that I'm going to stick on the left-hand side, and that's going to subtract my p of m and n plus 1. And on the right-hand side, I've got a p plus q times p of m and n. And so I get 1 in my p term and 1 in my q term, and they're off by a minus sign. So now I'm going to use the fact, so I'm going to take this and solve for dx dt, because that's going to be a function of the velocity. And I'm going to define a quantity d equals PQ times 2 times delta x squared over delta t. This is my diffusion coefficient. I'm going to do a little bit more algebra, and what I have. Let's talk about what I have. I have P of x and t plus 1 equals P of x plus 1 t times q minus P of x and t minus P of x minus x and t minus P of x minus 1 and t. Oops, I've got a minus P of x and t. So let me do this again. So P of x n plus 1, let's leave it as m plus 1 minus P of m n over delta t. What is this if I send n to a tiny number? What does this look like? Let me rewrite it again. So if I've got f of t plus delta t minus f of t over delta t, what is this? It's a derivative. So is this one. So now I've got a derivative at the top, yeah.
For the second term, down,
Here.
times q, like pretty low, yes. Is that p m plus 1 comma n?
Yeah.
Okay, thank you.
Sorry, this is n, and this is n. So on the right, so on the left-hand side, I have P of m and n plus 1 minus P of m and n. So this is just a difference in the time coordinate. So this term is going to turn into my time derivative. On the right-hand side, I got a p and a q, so I've got these two things separate. We'll do a little bit of algebra and make this work out better, but what I've got is a p of m minus 1 of n, m minus 1 of n, and m plus 1 of n. That's how I got here in the first place. And then I got a pmn and a pmn. So this looks like a spatial derivative, right? And this one also looks like a spatial derivative at a different point. So if we think about lattice points in space, if this is m, I'm taking this difference and I'm going to subtract this difference. So what is that? So if I have one difference, that turns into a derivative. Now I have the difference of derivatives is the second derivative, right? So this whole second term turns into the second derivative. So you take this velocity and you solve for delta v and delta x. So this velocity, it's got a p in it, it's got a q in it, it's got my delta x and my delta t in it. And you can see I've got a p delta x delta t and a q delta x delta t, and a little bit of algebra to do. And what this turns into is, where should I write it? I'll write it up here again. So then we're left with dp dt of m and n. Oh, now let's call this x and t now. So x is m delta x, and t is big N delta t. So I'm not really changing anything, I'm just kind of labeling things differently. Is equal to minus v times d by dx of p plus big D of d squared dx squared of p. So here's my partial time derivative. This is a velocity term. So I can put this over here, and this just becomes the full derivative. Right? Because it's just a v dot grad x equals d squared dx squared of p. So now, this random walk process looks like a diffusion process. It has this del squared p kind of process. So as time moves forward, the probability evolves with this dx squared, which you know, because of before, is going to evolve kind of like an exponent, like a Gaussian. So okay, so what have we done? So we've talked about random walks. We showed that the position, the variance in the position of my random walk is just going to be proportional to the n times some other stuff. We make a continuous distribution to make it look like a Gaussian, and we can connect it to the diffusion operator. So this is really the key that we're looking for is how does this diffusion operator behave? One can see that it behaves basically like a Gaussian, right? I haven't proven that yet. I will in a second. Well, no, I'm not going to prove it. I'm just going to show it to you. So now let's quick talk about what the Green's function is. So you guys done Green's functions? You've done Green's function somewhere?
Very, like a little bit, not
Okay.
first year.
We'll do, again, a little bit right now.
I've heard whispers.
So basically, if we were to look at this,
Yeah.
if the probabilities are equal of moving to the left and right, then over time we won't be essentially moving anywhere. We'll just be spreading, like our motion would be spreading out, but we won't be moving anywhere. But if the probability is biased towards one direction, over time we'll slowly be essentially estimatedly moving in that direction, but really slowly.
That's right, that's right, that's right. So this V is the asymmetry. Remember, V is P minus Q. So if I'm balanced and I have a probability of going to the left is the same as my probability of going to the right, then V is 0. And that term goes away. And you just have a thing that just spreads out in time. If you have a net velocity, then it shifts, it translates and spreads at the same time. Okay, I don't trust that clock. What time is it actually?
10:50.
10:50. Okay, that's okay. I only have 10 minutes worth of stuff to say about Green functions. So these things are incredibly powerful because if you have the Green's function for the operator, you can just solve your differential equation using the Green's function. And I had notes where I derived this, but I couldn't find them. So, and I only have 10 minutes. So let's just talk about what a Green's function is in the first place. So I have some linear operator L. So L is some linear operator. What does that mean when I say a linear operator?
That's a linear relationship.
Uh-huh.
You can distribute it.
You can distribute it. It distributes. So L of A plus BX equals L of A plus B L of X. So adding distributes and constants come out. Both of those things are important. So you have some linear operator, and del squared, all of your derivatives are all linear operators, and all your powers of derivatives are all linear operators, and integrals are linear operators. So there's a lot of things that that are linear operators that you can do things with. So the Green's function is the thing that gives you a delta function. So if I say my operator times my Green's function, this gives me some delta. So so the operator acts on functions of x. The Green's function is a function of two variables, x and x prime. So the operator is acting on x. The Green's function is a function of x and x prime. And this gives you delta x minus x prime. So, sorry, I usually do this before I get here, of thinking about what is the best way to explain the concept, but that's what I got. So this is useful. So then if I multiply this by, so what I want to find is L of u equals f. And I want to find u. So I have some operator that I'm acting on some function, and I have the result. I need to solve u by inverting this linear operator. So L times G equals a delta function. So L times G times U is equal to delta function times U. So if I integrate this, then the right-hand side is the integral of delta of x minus x prime of u of x, which is just u of x prime. And the left-hand side is sorry. Sometimes my flow sucks. LU equals F. So U equals the integral of G times F ds. So I can get, so I can invert this with my Green's function. Yeah, and I have more to say about that. I'm actually going to stop there and come back to this when my brain is not at least cooperating better. We'll talk about Green's functions next time when I have thought about it a little better. Have thought about the pedagogy a little better. We're running out of time. We got 5 minutes left. That's all right. Does anybody have any questions about anything other than the last thing that I kind of stubbed my toe on? Diffusion. So mostly the important bit is random walks and diffusion are connected to the diffusion operator, and we understand the diffusion operator. And that's all I'll say today.